Hi everyone, thank you for assisting to our talk. Today we'll talk about NTLM, reflection attack, a story of an accidental Windows RCE. My name is Wilfried, I'm with my colleague Guillaume. We both work at CNActive and we're doing pen test and red team assessments. So let's talk about the vulnerability. A vulnerability came out this year in June with a CVSS score of 8.8 and was classified by Microsoft for a Windows SMB client elevation of privilege vulnerability. We kinda disagree, we mostly think this is a remote command execution. Actually, this vulnerability is a trivial logical vulnerability that can be performed by authenticated users. It involves authentication reflection attacks, and it only works on machine that does not require SMB signing, so basically every Windows version except the latest one. The vulnerability was so trivial to discover and to exploit that it was found by at least 7 people or companies within a short period of time. Shout out to Red Team Pentesting that was the first to discover and report to Microsoft. I'm also wondering how many people discovered it and exploited by accident without realizing it was a bug. You will see why right after. Few words regarding our research motivation. We already know that there's a lot of bugs related to reflection attacks. For instance, there was a searcher mentioning that Kerberos relay is way more powerful than NTLM relay, and he showed a specific case targeting ADCS environment last year in Black Hat Asia. NTLM reflection attacks also have a lot of bugs. The first one came out in 2008, then 2009, 2015, 2019, and since then we thought reflection attacks were no longer a thing. And we'll see that was not the case. So before digging into the vulnerability, I will give you some core concepts, so everyone is on the same level in order to understand. The first core concept will be authentication coercion. Authentication coercion is when you force an identity, it can be a user or a machine account, to authenticate to a control server. There are several ways to coerce a machine into authenticate to a given server. Some are deterministic, some are not. The most popular one is to force to call an RPC service in order to access a file that points to an arbitrary file share. So we can illustrate that. On the top we have our target machine, and on the bottom we have the attacker laptop. So first we perform that RPC call. There's few functions that allow us to perform the coercion. One of the most well-known is EFS RPC encrypt files SRV. But what is important here is to notice there's a UNC path convention which points to a remote location, here the attacker IP. The RPC service on the machine will then talk to the SMB client, saying that, okay, you need to access this specific remote file. So the SMB client will perform an SMB connection to our attacker laptop. The attacker laptop will host a SMB server and try to perform the authentication workflow. So it will ask, please authenticate to us. The authentication workflow will then go on and we'll receive an authentication blob. This is authentication coercion. Another concept will be authentication relay. Authentication relay is then when you force a client to authenticate to a control destination, that was the coercion, and then you relay the authentication to another server. Here, for instance, on the attacker, we force the authentication coercion on the machine A, we receive the authentication blob, and then we relay this authentication blob to another machine here on the service on machine B. This way, we are not authenticated as the client from machine A on the service on machine B. Another concept will be authentication reflection. Basically, it's the same. This is a special case where the client and the server are on the same machine. We receive the incoming authentication blob and read it back to the same target. Microsoft describes it as a bug, so mitigation were in place in order to prevent relaying back to the authentication to the same machine. That was the reflection attacks. Last concept will be Kerberos authentication coercion. We know that NTLM relay is quite easy to perform, but actually for Kerberos it's more complicated. There's more requirements. The main difficulty is to receive the authentication blob, so the Kerberos authentication, which stands for an API-REC message. Kerberos is using tickets with service principal name, or SPN, with the following format. the CIFS/SRV1, for instance. SPN is constructed by the client based on the server hostname or fully qualified domain name, and the server hostname or FQDN is resolved through DNS, which is not under our control. So if you want to illustrate that, again, from the attacker laptop, we try to perform coercion using the Kerberos protocol, using the hostname, here SRV1. Then our target SRV1 will ask to the DNS server what is the associated IP address. It needs to perform DNS resolution. Now you know how DNS works. The DNS will now answer back to the client with the associated IP. And because this IP is its own, will not receive any incoming authentication and will do not receive an APREC message. So we thought at the start that Kerberos authentication coercion was not possible, until a well-known security researcher, James Forshaw, discovered that a Marshall credential target information structure can be added to the end of a SPN. LSAS, during the authentication process, will discard it before making the Kerberos ticket requests. So actually, when you request a ticket for CIFS/SRV1 following by the specific base 64 encoded string, it will actually return a SPN for CIFS/SRV1. And that specific base 64 encoded structure is the Marshall credential target information. And what is interesting also, we know that Kerberos is working with DNS, and that specific record is a valid DNS record. So how we can exploit that for Kerberos authentication coercion? First, we register that specific DNS record. What is interesting is that in Active Directory environments, any authenticated user can create this specific record. We force the machine into authenticate to that record. It will point to our attacker IP using the SMB protocol. And then we will receive an APREC message for the SPN that we want. So again, we can illustrate that with the same scenario. First, we add the DNS record, SRV1 following by the Marshall target information structure. It will point to our attacker IP. Then we perform the authentication coercion using that specific crafted DNS record. Again, the machine will ask to the DNS server what is the associated IP address. The DNS server will answer with the attacker IP. And then we will receive the incoming authentication with an APREC for the SPN that we want. This is how Kerberos authentication coercion works. Okay, so now you have the concepts. We can talk a bit more into the vulnerability discovery. So at the start, we were performing some Kerberos research during reflection attacks, and we know that some check and protection against reflection attack may be based on names. So we try to fiddle with the target name during coercion. And something interesting happened when we tried to perform coercion to that specific DNS record using the Marshall target information structure. On the top, I'll perform the coercion using Petipotam with a low privilege user and that specific DNS record. And at the start, I'm trying to perform a Kerberos relay reflection attack. So I'm using the dedicated tool from Impacket, which is an offensive Python suite. So carry relay.rx.py. And when performing the coercion and receiving the APREC to my control server, I received this weird error message, unsupported MEC type NTLM SSP. I was quite confused because I'm not trying to perform any NTLM authentication. I'm only using hostname or fully qualified domain name. And basically, most of the time, Windows prefer Kerberos authentication over NTLM. So I was quite surprised, and I say, okay, if Windows wants to perform NTLM authentication, we can do that. I can use the dedicated tool from Impacket that performs NTLM relay, which is called NTLM-relay.py. So I do the same. On the top, I'm performing the coercion, which is the same command. And on the bottom, I start NTLM-relay.py, targeting the same server. And to my surprise, the authentication first succeeds, and also it gives us a privileged SMB session. Here, by default, NTLM-rex dumps the local SAM hashes. So I was quite confused. I say, okay, something is weird is going on. Reflection attack are patched. This should not be working. I know there's some specific registry keys that can allow this specific behavior, but it was not the case in my lab. This registry key was not set. So at first I thought there was something not going on well in my lab. So I asked to another colleague, I say, okay, I have this strange behavior, can you test on your own lab? At first he was thinking I was bluffing, he said, no, this can be real. And before telling me I was bluffing, he tried on his own, he said, okay, what the fuck, what is going on? It works, and we were privileged. So basically this is how we discover the vulnerability by accident, by performing researches. But we cannot let the things like that. We have to understand why does it work, what is the root cause. So during performing the analysis, I want to perform first a network analysis and perform network diffing. So on the left, I will do the same attack, but instead of using the specific crafted DNS record, I will use the IP address of my attacker laptop. So basically, I'm trying to perform reflection attack, but using my own IP. On the right, it will be using that specific DNS record that makes the attack work. And during the NTLM exchange, on the NTLM SSP challenge part, we can notice two differences. On the left, we can see that there's some specific flag that is not set. It's a bit small, but it doesn't matter much. And on the right, you will see also that specific flag, when using the specific DNS record, it will be set. Also, on the left, when we are performing using the IP address, we can see that there's a field called reserved, which is empty. And on the right, this field is not empty anymore. It has a value. So basically what's going on the left, we are performing standard NTLM authentication. And on the right, we are performing a local NTLM authentication. The flag that was set on the right stands for local authentication. So we have to understand what is local NTLM authentication. Local NTLM authentication will happen when everything is going on the same machine. So first, the client will perform initial security context. It will discuss with LSAS and the dedicated provider, here NTLM SSP. The authentication workflow will start. The NTLM SSP will answer back to the client. It will start the NTLM exchange by performing the NTLM negotiate message. And then the client will forward this message to the service. Moving on, the service will now discuss again with the NTLM SSP, always within the same machine, and it will perform accept security context during the NTLM negotiate message. And within the memory of the NTLM SSP, it will create a new context within a local context list. It will create a new structure with a specific identifier, for instance here, 10,002. Moving on, we continue the NTLM authentication workflow. The NTLM SSP will now answer the NTLM challenge back to the service. And within this challenge, it will specify the context ID. And then the service will forward the NTLM challenge back to the client, again with that specific context ID. And this is what we could see in Wireshark. We could see that specific context ID in the reserve field. Also, it will set the flag for local authentication. Moving on on the authentication process. Now the client will perform initial security context when receiving the NTLM challenge. Because now it have the context ID, it can within the memory of the NTLM SSP, it can add its token handle to that specific structure. So now within the memory of the NTLM SSP, on that specific context ID, we have the token associated to the client. Next, we'll finish the last part of the NTLM authentication. NTLM SSP will now send back the NTLM authenticate back to the client. Basically, this message is almost empty because there's no need to compute the challenge since we are performing local authentication. And then the client will send back the NTLM authenticate to the service. The last part will be the service discussing with NTLM SSP. It will perform accept security context, and it will still use the same context ID. And now, because the service can find this specific context ID, the authentication will succeed, and it will use the token handle associated to the client that was provided previously. So when we are performing network diffing, we can see that we are relaying a local NTLM authentication over the network. But why does the server decide to perform local NTLM authentication? I will let Guillaume explain that.
So to actually understand why the servers decide to perform local authentication, it's actually important to understand what happens when the SMB client wants to authenticate to the DNS record with the base64 marshaled credential information. So first of all, it will build an SPN of the form CIFS/the DNS record, the DNS record. It will try to initialize a security context, which will actually be a call to the device driver ksecdd. The call will be routed to LSA SRV. And then the magic will happen here via a call to LSAP check marshal target info, which will actually check inside the SPN if there is a marshaled credential information. And if yes, it will strip it off the SPN. So afterward, the context initialization will be routed to the correct SSP, in this case NTLM, and the SPN will just be CIFS/SRV1. Another thing to understand is what we call NTLM local authentication hinting. Basically, when the NTLM client builds the first message to authenticate, it can decide whether or not to hint the server into performing local authentication. So the decision process is what you see now on the screen, and I will illustrate it with a few examples. So the first example is if you try to coerce a machine by giving it an IP address as the target. The SPN that will be constructed will be CIFS/the IP address. Via a call to SSPR get target hostname, the service class will be stripped off. You will be only left with the host part. In this case, it's the IP address. And now it will go through a series of checks. The first one being, is the target either the host name, the FQDN, fully qualified domain name, or the string localhost? In this case, it's false because it's the attacker IP address. The second check will be, is the target one of the local IP address of the machine? It's also false. So the conclusion for this scenario will be to not hint the server into performing local authentication. But if you take another example, let's say you coerce a machine into authenticated with the DNS record with credential marshal target information. As we saw earlier, the base64 data will be stripped off the SPN and will be only left with CIFS/SRV1. The host part will be extracted from the SPN, so we are only left with SRV1, and now we'll go through the same series of checks. So is the target either the host name of the machine, the FQDN, or the string localhost? In this case, it is. SRV1 is the host name of the machine. So we'll go to the right. Are we requesting a null session? We are not. Did we provide explicit credentials? No, because we are using Windows implicit authentication. So the conclusion is to hint the server into performing local authentication. So depending on how you coerce the machine, you'll get different behavior from the NTLM client. So the next thing to explain is what actually is local authentication hinting. It's quite easy to spot if you do a little bit of network diffing again. So on the left, the client does not hint local authentication, and on the right it does. Basically, the only thing that changes is that the two fields, calling workstation domain and calling workstation name, are null on the left and are filled with correct values on the right. So local authentication hinting is just including the machine information inside the first NTLM message. And when the server receives this message, it will parse these two values and will decide or not to perform local authentication. So to sum it up a bit, first, LSAS discard the credential target information of the target. So SRv1 plus base64 data just becomes SRv1. The NTLM SSP client identifies that SRv1 is the local machine, so it will hint the server into performing local authentication. And the NTLM SSP server retrieves these values, compares it with its own values, and decides to ask the NTLM client in the third message to perform local authentication. There is just one last question for NTLM, is why do we get a privileged SMB session? Well, it's kind of easy with what we just explained. The NTLM client runs in the system process, which runs as NT authority system, which means that when the service will try to impersonate the client, it will impersonate the token of NT authority system, which will give us administrator access on the target. So to illustrate it, we've prepared a small video to show you how easy the vulnerability is to exploit. On the top left, we'll start our relay server. When it receives the connection, it will actually upload a binary and run it via the service manager. On the bottom, we start a reverse shell listener. And on the top right, we'll prepare our authentication coercion with Petit Potam. You'll see that we use a low privilege user account and that we coerce the machine into authenticated to the record with the base64 data. So we'll trigger the coercion. We'll receive an authentication on the top left. You'll see that the relay succeed, which will upload a binary and run it via the service manager. And on the bottom, you see that we get a system shell on the machine that we coerced, which is workstation 1. So that's it for NTLM. But we also wanted to know if it would work on Kerberos, and actually the answer is yes. The vulnerability also affects Kerberos. The only thing to keep in mind is that your relay server must not advertise NTLM when you receive the first SMB connection, because there is a specific case for the negotiate SSP which the SMB client uses, which will prefer NTLM over Kerberos only in the case of local authentication. So, what does it look? First, for Kerberos, first you coerce the machine into authenticated to the base64 DNS record. The machine forges an AP rec and sends it to you. You take the AP rec, you forward it to the SMB service, and you get a privileged session. Two things to note. The SMB client runs as NT authority system, as I said. So every network authentication that will be done as the machine account, SRv1 $. So we are actually relaying the machine account. If you know a bit about machine accounts in Active Directory domains, you'll notice that something is weird. The machine account is not privileged on its associated machine. So that's a bit weird that we actually received a privileged SMB session. To understand it, we must do a little bit of reverse engineering of the Kerberos SSP, which I will explain now. So, when the SMB client wants to authenticate via Kerberos, it will use initialized security context to contact the Kerberos SSP, which will create what's called a subkey entry. It will, which contains various information about the client. It will generate a random subkey, and it will also store the token handle of the client. It will then include this entry into a subkey entry list, which is a global list that the Kerberos SSP maintains. It will forge an AP rec, include the previously generated subkey inside, and send it to the client. The client will forward the AP rec to the service, and the service will validate the AP rec by asking the Kerberos SSP. The Kerberos SSP will decrypt the AP rec and compares the subkey with all the entries in the subkey list. If it finds an entry with a matching subkey, it will consider that the identity of the client is pointed by the token handle that was stored. So whenever the service will try to impersonate the client, it will impersonate the token handle that was stored in the subkey entry. Which explains why we get a system session. The last part of this talk will be about the patch. So when Microsoft issued the patch, we were curious about how they fixed it. Did they issue the patch for each protocol? Did they manage to do something global? To know where to look, we remember that in the official advisory, the vulnerability was labeled as Windows SMB client elevation of privilege vulnerability, which means that the fix should be in the SMB client, which is partly implemented in MRX SMB.sys. We did a bit of patch diffing, and it was quite easy because only one function changed, which is SMB CE create SRV call, which is called when trying to access a resource over SMB. The check is actually quite simple. It will parse the target, and if it contains a marshaled credential target information, it would just abort the connection. So you cannot coerce a machine with this kind of record anymore. That's how they fix the vulnerability. And finally, to conclude, by doing this research and this presentation, we wanted to highlight that high-impact, simple, and stable logical vulnerabilities still exist in Windows. In our opinion, mitigations such as SMB signing are still underrated. In this very specific exploitation scenario, it would have blocked the vulnerability, but it is still not enabled by default on Windows, except Windows 11. So now that this vulnerability is fixed, is it the end of authentication reflection vulnerabilities? Well, as you may have guessed, the answer is no, but that will be for another talk maybe. Thank you for listening.
Thank you very much for that very interesting story, very enlightening. Do we have questions from the room? We have time for one question. Yeah, we do. So we do have a cube. Maybe somebody can get that so everybody can hear you clearly as well. Thank you very much.
So since they only fixed the coercing part, would this attack still work if I control the DNS entry for the target system?
You could, if you can control the DNS, you could trigger Kerberos authentication. The thing is, later in the year, so I think it was in October, Microsoft issued another patch for a different vulnerability using a partial control over SPN, which is kind of an equivalent to controlling DNS. And now, if you receive a local authentication from an IP address that is not a local IP address, the SMB server will just deny the connection. So it would have worked before October, but now it doesn't.
Thank you. Great talk.
Awesome. Thank you very much. So in case you have further questions, because I'm pretty sure you do, I think you two can be found outside in front of the room. So catch them, get a chance. And for now, before we head into a short break, it's just 10 minutes. So we'll go to Munich in like 16:40. The next talk starts. But before that, let's give another huge round of applause here. Thank you.
Thank you.